So the second video in section 10.4 and final video is about how to find the arc length of a polar curve. So in order to do this, we want to think about the polar curve in terms of the parametric equations like we have in the past, where x is r cosine theta and y is r sine theta. And as a reminder, to find dx d theta and dy d theta using that form, we use the power rule. I'm sorry, the product rule, not the power rule, because it is r times cosine theta and r times sine theta. And again, we've seen that in 10.3, so this is repeating or as a reminder of how to do the derivatives of x and y individually. So that, along with the knowledge of cosine squared plus sine squared being 1, which of course is Pythagorean's theorem, we have a way to derive arc length for ourselves, because remember, arc length is using Pythagorean theorem in the original Cartesian coordinate system version of arc length. So if you follow this slide along, we have dx d theta squared, because that's cosine squared, and dy d theta squared is sine squared. Filling in the blanks, we have dr d theta squared cosine squared, which is our part of our dx squared. And down here on the next line, you'll see you have also dr d theta, but with the sine squared. So this comes from taking the formulas from dx d theta and dy d theta on the previous slide and squaring each one of those out using the FOIL method or whichever method you're comfortable with. And that's why we end up with so many terms on this page. But luckily, all of this, because of a minus sign here and a plus sign here, simplifies all the way down to dr d theta squared plus r squared. When we add these two terms together, you'll notice that you can factor out the dr d theta squared, and what you'll be left with is sine squared plus cosine squared, which is just 1. So this just becomes dr d theta squared. The same thing happens with these final two terms, which is why it just becomes r squared. So the sum of the squares of the individual derivatives turns into dr d theta squared plus r squared. So that allows us to translate the parametric form of arc length into a polar form. So with parametric, we had dx d theta squared plus dy d theta squared, all under a square root. So translating that for polar form, we have r squared plus dr d theta squared, all under the square root. And this is the formula for arc length for a polar curve. So let's look at an example. Let's try to find the length of the curve r equals e to the 7th theta, and we want the length from 0 to 2 pi. So using the equation we just found on the previous page, we know it's going to be the integral from a to b of the square root of r squared, which is our function, plus the derivative of the function squared. So we're told that we want to go from 0 to 2 pi, so that's our limits of integration. R squared becomes e to the 7th theta squared, and dr d theta squared becomes 7e to the 7th theta squared. Where is that coming from? If you look at the formula, r equals e to the 7th theta, and you take the derivative of that, straightforward. What's the derivative e to the 7th theta? It's e to the 7th theta, but times 7 because of the chain rule. So on the bottom here, we have that final, we have the arc length formula filled out. So e to the 7th theta squared is r squared, and 7e to the 7th theta, which is dr d theta squared. So now that you have r squared filled out and dr d theta squared filled out, the rest of the problem is the calculus part. Figure out what the antiderivative is. So when you square e to the 7th theta, that's e to the 7th theta times e to the 7th theta, that becomes e to the 14th theta. So for the second term, the same thing happens, except we also have a 7 squared. So we end up with 49e to the 14th theta. Well, these have the same terms, e to the 14th theta, so we can add them. So we have 1e to the 14th theta plus 49e to the 14th theta. Those add together to make 15e to the 14th theta. Sorry, 50, not 15. Remember, you can only do this when the exponents are the same. We have e to the 14 theta here and e to the 14 theta in the second term. So we're able to add them. They are like terms. So 1 plus 49 equals 50. Now that we don't have a sum or a difference underneath the square root, we can split up the square root. So we have the square root of 50 times the square root of e to the 14 theta. Well, the square root of e to the 14 theta would be e to the 7 theta, which is basically the reverse of what we did on the previous page. On the previous page, we squared e to the 7 theta to get e to the 14 theta. So when you go backwards, you end back up at e to the 7 theta. So now that we're at this step, we're ready to find the antiderivative. And again, you're going to use the opposite of the chain rule. E to the 7 theta antiderivative is e to the 7 theta divided by 7 or multiplied by 1/7, whichever you're most comfortable with. So we have that square root of 50 divided by 7 times e to the 7 theta. And so once you plug in your limits of integration, 0 and 2 pi, you end up with square root of 50 over 7 times e to the 14 pi minus 1. And that's the final answer for arc length for the curve r equals e to the 7 theta.